excited to do my lab about collisions, and some important concepts that we know about collisions are the 3 different types, those being elastic, inelastic, and perfectly elastic. Something important to note about these is that elastic is the only type of collision where energy is conserved. However, all types of collisions conserve momentum. So some equations that we use in our calculations is the equation for momentum, that being mass times velocity, the equation for the change in momentum, that being final momentum minus initial momentum, and that should be equal to 0 because we know that momentum is conserved. And we also take a look at kinetic energy, and the equation for that being 1/2 mv squared. So this is our observation video in Tracker. It's just an elastic collision between 2 carts on a track. This was just a video that I found on YouTube from a YouTube channel called Physics Demos. So thank you to them for this. So for the model code, we first initialized a 2-mass system, and these just being 2 spheres with a radius equal to half of the length of the carts. We also initialized 2 different graphs, these being the change in momentum and change in kinetic energy that we will plot to later. We also initialized the velocity and positions using the data from Tracker. I just found the average velocity of each of the carts when they were in motion and the initial position of each cart from Tracker. Both of the carts' masses were initialized to 0.05 kilograms because they were identical, and this was the mass that we found on the internet about these carts. We also had to split our code up into 2 different while loops, the first while loop being before the collision, and we did that by setting doing while the position of the ball 1 plus the radius was less than or equal to the position of ball 2 minus the radius. Then for our second while loop, we just did this for while the position of the second ball was less than the final position that we found in Tracker. Within both of these loops, we used the position update formula to update the position of each ball. We assumed a constant velocity and disregarded the friction force because the friction forces on these cart track systems is relatively low. We also updated the change in momentum and the change in kinetic energy and graphed both of these values to the graphs we initialized previously. Here's a video of the model once the code was completed. As you can see, the 2 balls bump into each other and the first ball stops, and then the second ball starts in motion, just as we saw in the Tracker video. So from the graphs we initialized in GlowScript, we can see that the change in kinetic energy and change in momentum remains constant at 0. This makes sense because with elastic collisions, kinetic energy is conserved, and with any collision, momentum is also conserved. We also did a graphical analysis on position versus time, the blue line being the model position, and as you can see with this, it did have a constant velocity because the slope is constant. However, with the dark blue line, for the experimental position versus time, you can see that the experiment velocity was not constant. This is mostly due to human error in Tracker, but it can also be due to frictional force and a small loss of energy due to sound. Some important questions we should keep in mind is what if the carts did not have identical masses? This would mean that the velocities would not be the same for each cart. The cart with the heavier mass would move slower and vice versa to conserve momentum. However, what if the carts stuck together? This would be a perfectly elastic collision, which means kinetic energy would not have been conserved. The velocity after the collision would have also been slower to conserve momentum and account for the larger mass of the system. Thank you for watching.